Hello everyone, my name is Yu and I'll give you an introduction to our paper Streaming and Small Space Approximation Algorithms for Edit Distance and Longest Common Subsequence. This is a joint work with Kuan, Alireza, Mohammed, Zhengzhong, Cheng, Aviad, and Saeed. So let me first give a brief introduction to the problem studied in this work. So the edit distance between two strings x and y is defined by the minimum number of insertions, deletions, or substitutions that is required to transform x to y. So for example, here we can first insert a symbol t after first two symbols in x, and then substitute this g with an a, and finally delete the last symbol g. And you can check that this is the optimal way to transform x to y. So the edit distance between x and y is 3 in this example. The second problem we studied is called longest common subsequence. It also takes two strings as input. And for example, here the longest common subsequence is labeled in red, and it has length 5. Both edit distance and LCS are fundamental problems in computer science. They have been studied extensively in the past few decades. We now give a brief overview of some of the results. The classical dynamic programming algorithm can solve both problems in quadratic time. For input of length n and edit distance bounded by some parameter k, we can solve the edit distance in big O n plus k squared time. The best algorithm in terms of time complexity currently is only slightly subcorrected time by a factor of polylog n. We also know that all these algorithms needed at least linear space in worst case. Recently, the study of fine-grained complexity gives some conditional lower bound for edit distance and LCS. For example, Barkers and Indike show that any truly subcorrected time algorithm for edit distance will contradict the strong exponential time hypothesis. A recent line of work gives breakthrough in fast approximation algorithms for edit distance. Chakraborty et al. First gave a constant factor approximation algorithm for edit distance in truly subcorrected time. It is further improved to near linear time by Andoni and Nosetsky. That is, there's an algorithm that can give constant factor approximation for edit distance in big O n to 1 plus epsilon time, where epsilon can be any small constant. We know that all these known algorithms in subcorrected time are randomized. So all these results are mainly focused on the time complexity. So what about space complexity? First, it is not hard to show that both edit distance and LCS are in non-deterministic log space. Thus, by Savage theorem, both can be solved in big O log n squared bits of space deterministically in quasi-polynomial time. How about polynomial time algorithms? The best algorithm we know so far uses big O n times log n to 1.5 over 2 to the square root of log n bits of space, which is slightly sublinear. So far, there's no algorithm that can achieve both truly sublinear space and polynomial time simultaneously. So in this work, our focus is on designing space-efficient approximation algorithms for edit distance and LCS. Specifically, we consider two different computation models. The first one is called a symmetric streaming model. We will give an introduction soon. And second one is a standard random access model. Before introducing the asymmetric streaming model, we first give an overview of the results in the standard streaming model. In this model, there are strong lower bounds. For example, for randomized algorithms, if we want to compute edit distance and LCS exactly, it would require linear space. And for deterministic algorithms, even to get a 2 over square root n approximation of LCS, it would require linear space. On the upper bound side, streaming algorithms for edit distance have been limited to the case that the edit distance between the input strings is bounded by a parameter k, which is substantially smaller than n. We know that there exists a randomized algorithm that computes edit distance in big O k cubed times polylog n space. In this work, we consider the so-called asymmetric streaming model. It can be viewed as the intermediate model between random access model and fully streaming model. It is first studied by Sachs and Sesh in a 2013 paper. In this model, we assume we have streaming access to an online string X and random access to an offline string Y. Sachs and Sesh give a 1 plus epsilon approximation algorithm for n minus LCS with roughly square root n space. It can be shown that eddy distance can be reduced to n minus LCS in this model. Thus, this already gives a 1 plus epsilon approximation algorithms for eddy distance. We now give an overview of the results presented in our paper. First, for the symmetric streaming model, we show that there exists a constant approximation algorithm for eddy distance that uses only roughly n2 delta space for any small constant delta. And for LCS, there's a 1 minus epsilon approximation algorithm that uses roughly square root n space. For a non-streaming random access model, we show that there exists algorithm that can achieve 1 plus or minus small o1 approximation of both eddy distance and LCS with polylog bits of space in polynomial time. So before presenting our algorithms, let me first briefly introduce the key ingredient of our algorithm. The first one is the triangle inequality for eddy distance. The eddy distance is a metric, and we have the following triangle inequality by definition. That is, for any three strings x, y, z, the eddy distance between x and y is smaller than the eddy distance between x and z plus the eddy distance between z and y. The triangle inequality has been shown to be very important for designing subcredit time algorithms for approximating eddy distance. Our algorithm for eddy distance in the asymmetric streaming model gives yet another novel use of triangle inequality. The second ingredient is recursion. We show that, just like the proof of Selfish theorem, recursion can be very useful in designing space-efficient algorithms for eddy distance and LCS. Okay, now let me first introduce our algorithm for eddy distance in a symmetric streaming model. So in this model, we have streaming access to an online string X and random access to an offline string Y. Our algorithm first divides the online string X evenly into B blocks. Then, for each block Xi, if we can find the substring Yi in Y that has the smallest eddy distance to Xi, then we can show that by triangle inequality, the summation of the eddy distance between Xi and Yi plus the eddy distance between Y and the concatenation of Y1 through Yb is at least the eddy distance between X and Y, and at most 3 times the eddy distance between X and Y. So this would give us a 3 approximation of eddy distance. We note that for eddy distance between Y and the concatenation of Y1 through Yb, if we want to compute it exactly in polynomial time, it would require linear space or small space with quasi-polynomial time. To get a polynomial time algorithm, the idea is to replace the exact computation with our small space approximation algorithm, which will be introduced later. If we take b equal to square root n, then each block xi would have length roughly square root n. Thus, with roughly square root n space, we can find for each block xi a substring in y, say yi, that is closest to xi in eddy distance. So we only need to remember the starting and ending point of this yi, and also the eddy distance between xi and yi. Thus, this can give us the 3 approximation of eddy distance between x and y with roughly square root n space. We can further reduce the space complexity with recursion. That is, for each block xi, instead of finding the closest substring, we turn to an approximate solution. That is, we find the substring yi and a value di. We say it is the alpha approximation to the closest substring if that the eddy distance between xi and yi is the most di, and di is smaller than alpha times the eddy distance between xi and any substring of y. Now, for each block x, if we can find yi and di, that is an alpha approximation to the closest substring. Then, by triangle inequality, we can show that the summation of di plus the eddy distance between y and the concatenation of y1 through yb is a 2 alpha plus 1 approximation of edit distance. This allows us to design a recursive structure. At each recursive step, we divide the online string x into n2 delta blocks, and for each block, we recursively find an approximate solution to the closest substring. The recursion stops when the online string has length smaller than n2 delta. In that case, we find the closest substring exactly. The depth of this recursion is 1 over delta, and for each recursive level, we lose a factor of 2 in the approximation factor. This gives us a 2 to big O 1 over delta approximation with roughly n to delta space. So that is our algorithm for edit distance. We now introduce our algorithm for LCS. The algorithm first divides the online string x evenly into square root n blocks. It maintains an array D with size log n with base 1 plus epsilon star. Here, epsilon star is picked to be epsilon over square root n. So if epsilon is a constant, the size of this array D is roughly square root n. The algorithm processes x from left to right, block by block. After processing block xi, it updates D so that the case element of D, say dk, stores approximately the smallest index, such that there is a longest common subsequence between the first I blocks of x and the first dk symbols of y, with length at least 1 plus epsilon star to k. So for each update of D, we do the exact computation. We know that by our choice of this epsilon star, each update of D will lose at most an epsilon over square root n fraction of the length of LCS. So this is guaranteed to output an 1 minus epsilon approximation of LCS. We now turn to the standard non-streaming random access model. We first introduce our algorithm for approximating edit distance with small space. For analysis, let's assume that we know a parameter k that is close to the actual edit distance. Although such a k is not known, we can try every k equals to 1 plus epsilon to j for any possible integer j. Our algorithm guarantees that when k is close to the edit distance, the output is a good approximation of edit distance. And for any k, the output is always at least the actual edit distance. Given such a parameter k, we know that in the optimal alignment, every symbol in x is matched to some position in y, that is at the most k from its position in x. This observation allows us to design the following algorithm that is proposed by Hajiaghayi, Seddighin, and Cheng in a 2019 paper. So we first divide the input string x into b blocks. Then, for each block xi, we can pick b over epsilon squared times log n candidate blocks, such that if we know the edit distance between xi with each of its candidate blocks, then a dynamic programming gives a 1 plus epsilon approximation of edit distance. To further reduce the space complexity, we use recursion. So if the input string x has length larger than b, then we divide x evenly into b blocks, and we compute the edit distance between each block and its candidate blocks with our algorithm recursively. If the input string x has length at most b, then we do the exact computation. The depth of this recursion is at most log n with base b. For the degree of recursion, we know that there are b blocks, and for each block, there are b over epsilon squared times log n candidate blocks. And also we need to try log n over epsilon different case. So the degree of the recursion is b squared over epsilon cubed times log n squared. Notice that at each recursive level, we'll lose a factor of 1 plus epsilon in the approximation factor. So the final output will give a 1 plus epsilon to d's power approximation of the edit distance. For space, at each level, it will require b over epsilon times log n bits. The running time is dominated by the computation at the bottom level. Thus, we can get the following two sets of results. If we pick B to be log n and epsilon to be 1 over log n, then we get an algorithm that outputs a 1 plus small o1 approximation with big O log n fourths over log n bits of space. The running time is roughly n to 7th. If we pick delta and epsilon to be small constant and let B to be equal to n to delta, then we get an algorithm that outputs a 1 plus epsilon approximation with roughly n to delta space and roughly quadratic time. We now turn to our small space algorithm for LCS. Before doing that, let's take a look at a related problem called longest increasing subsequence. It takes one string as input, and the string is defined over a totally ordered set. It asks us to output the length of the longest subsequence that is in increasing order. Our algorithm for LCS relies on the following reduction to LIS. It works as following. We first define a new sequence, sigma, and when we read a new symbol x, we find all the positions this symbol appeared in Y. Then we add these positions to sigma in a descending order. We can show that every increasing subsequence of sigma corresponding to a common subsequence of x and y. We know that the new sequence sigma can be much longer than both x and y. The length of sigma is bounded by n squared. There is a classical algorithm solving the longest increasing subsequence problem called patient sorting. The idea is to maintain an array P where the ith element Pi is the smallest symbol such that there is an increasing subsequence with length I ending with Pi. The algorithm solves the problem in n times log k time, where n is the input length and k is the length of LIS. The space complexity is bounded by k times log of the size of alphabet. A previous work by Gopalan et al. Shows that there is a 1 minus epsilon approximation algorithm using roughly square root n space. The idea is to first divide sigma into square root of epsilon n blocks. Then we run patient sorting on sigma. After processing each block, we specify the array P. By maintaining an array P with size roughly square root n, we can guarantee that after each specification, we lose at most square root of epsilon over n times k in the length of increasing subsequence we find. Thus, this gives a 1 minus epsilon approximation. So the nature ideal is to use recursion again. If the input sequence sigma has length at most b squared, then we can compute a 1 minus epsilon approximation directly. Otherwise, we divide sigma evenly into b blocks. For our purpose, we need to maintain a specified array P with size roughly b of epsilon, such that after processing the first I blocks, we have the following property. The number k is roughly the length of the longest increasing subsequence in the first I blocks of sigma, and pk stores the smallest symbol so that there is an increasing subsequence with length k ending with pk. Similarly, for every j epsilon over b times k, there's an increasing subsequence with this length ending with a corresponding symbol in p. The problem is that the length of each block can be as large as n over b, which can be much larger than b. Doing exact computation will require roughly n over b space, and it is not clear how to use recursion. We now give a bit more detail. Assume that after processing block sigma I, we get a specified array Pi with size b of epsilon. Then, to compute Pi plus 1, the idea is to do it in multiple passes. And the first step is to compute a new k, which is roughly the length of longest increasing subsequence in the first I plus 1 blocks. Intuitively, k prime is the length of the longest increasing subsequence that can be extended from Pi. Thus, we can do the following. For each s smaller than k, that is a multiple of epsilon over b times k, we find the longest increasing subsequence of sigma I plus 1, with first element larger than the corresponding symbol in Pi, and then we take the maximum. The next step is to compute the middle element in the array Pi plus 1. For analysis, assume pi is one of the longest increasing subsequence of sigma, and pi can be divided into b blocks, such that pi I is a subsequence of sigma I. To compute pi I plus 1, a natural ideal is that for every s less than k and is a multiple of epsilon over b times k, we compute the longest increasing subsequence in sigma I plus 1, but only consider symbols larger than the corresponding symbols in pi. However, there may be a problem here. This is because the length of pi I plus 1 can be much smaller than the longest increasing subsequence in sigma I plus 1. Doing this may not give a good approximation of pi I plus 1. To overcome this problem, we do the following. We consider only increasing subsequences of sigma I plus 1 with length at most L, for L equal to 1 plus epsilon to j for some integer j. Analysis shows that this is enough to guarantee that we give a good approximation of pi I plus 1. These ideas are enough to give us a small space approximation algorithm for LIS. The analysis is similar to our algorithm of edit distance. The degree of recursion is bounded by b squared over epsilon squared times log n, and depth of recursion is the most log n with base b. We can get an approximation ratio of 1 minus epsilon to this power, and space required at each level is bounded by b of epsilon times log n bits. The running time is dominated by the computation at the bottom level. Our algorithm for LCS is obtained by reducing to LRS. Let sigma be the sequence we get after reducing LCS to LRS. Now instead of dividing sigma evenly into b blocks, we divide one of input string x evenly into b blocks, and then we divide sigma correspondingly. We know that dividing sigma in this way gives us some slight improvement in running time. Finally, similar to the case for edit distance, we can get the following two sets of results. If we take b equal to log n and epsilon equal to 1 over log n, then we can get a 1 minus small o1 approximation with polylog bits of space for both LCS and LRS in polynomial time. If we let delta and epsilon be small constant and b be n to delta, then we can get a 1 minus epsilon approximation with roughly n to delta space. The running time for LCS is roughly n to 3 minus delta. The running time for LRS is roughly n to 2 minus 2 delta. Finally, let me introduce some open problems that we find particularly interesting. First, for 1 plus or minus approximation of edit distance and LCS in the symmetric streaming model, we can only get algorithms using roughly squared n space. Can we prove strong lower bounds for this model? Second, all our algorithms are deterministic. It will be interesting to see if randomness can help design better algorithms. For example, algorithms with better space complexity in the asymmetric streaming model, or in the non-streaming setting, algorithms that can achieve Socratic time and small space simultaneously. Third, are there conditional lower bound for the space complexity of exact computation? We know that there is a so-called linear space hypothesis proposed by Yamakami that conjectures some NL complete problems cannot be solved simultaneously in truly sublinear space and polynomial time. It will be interesting to see if we can reduce one of these problems to edit distance, or LCS. That's all for this presentation. Thank you for listening. Bye-bye.